All right, welcome back, everyone. Not going to waste too much time since we really just, dipped one toe into 6.5, our last section for the test on Chapter 6. And remember that Chapter 6 test will be excluding 6.4. I know I said I was going to upload just kind of some basic notes and problems from that section, but I haven't done it yet. I will do it. But since you're not being tested on it, I don't feel stressed to get it to you with any kind of urgency. But I will get it at least before the test. So I said that if we can get everything done in the time I'd like to, spend 2 class periods working on 6.5, that puts us as having our test on the 9th and 10th. But I can't commit to that yet. I'm pretty sure that's what we're going to hit. But we'll find out, won't we? Okay, so reminder, sine, cosine, cosecant, and secant have periods of 2 pi, whereas tangent and cotangent have a period of pi. That issue will come up. If your solutions have a domain that isn't restricted, you must consider the periodic nature of those functions, which that will definitely come up, and this all goes together. So if you don't have a restricted domain, so if I just say solve, and I'll say solve from 0 to 2 pi, then whenever you do your sines, cosines, cosecants, or secants, your solutions, you have to add this 2 in pi because there are infinitely many answers. Every time you go another 360 degrees, the answer is still true. For tangent and cotangent, it's every time you go another 180 degrees, the answer is still true. So that's what this represents, because we can let n be any number. It can be 0. It can be 1, it can be 2, it can be 3, and then there's our first, second, third, and fourth solutions, whatever. So again, all that's paired together. Some techniques that we'll be using, if there's only one trig term, isolate it, and then you'll have something like sine of 30 degrees is equal to a half, and then you can use your triangles, your quadrilantals, your smart trig class, all that stuff to piece together your solutions of what the angle should be. Sometimes the inside won't just be a theta, it might be a 2 theta or a 3 theta or a 4 theta, or it could be x, it doesn't have to be theta. And then we'll have to go through this n equals 0, 1, 2, 3 process, and this will actually come up in another instance as well, but let's just label it for now, we'll get back to it. Let's see, and that's until you go past one period. So once your answers go past 360 degrees or 180 degrees, depending on which trig function you're using, then you're just going to be repeating yourself, basically. So then you just say, well, I'll add the n pi or 2 n pi, or don't, depending on the scenario. Okay, factor if possible, that can help us. Use double angles and or Pythagorean identities. That can be helpful. Now you might say, well, what about half angles? Admittedly, we won't do any with half angles. You might say, well, what about the sum and differences? Admittedly, we won't be doing any of those, but yes, you are right. All of those things could help you potentially, depending on the type of problem you have, but we're going to keep them, and I'm going to say on the simpler side of things, but that doesn't mean you're going to think they're simple. I'm just saying in the grand scheme of things, we're going to be keeping it simple. Watch out for extraneous solutions, which means you get a solution, but it doesn't actually work. Kind of like if you had a rational equation, which means there's fractions with x's in the bottom, maybe x equals 3 looks like a solution, but when you plug it in, it makes the bottom 0, and you can't divide by 0. That makes it extraneous. It means it looks like it works, but when you actually try and verify, it doesn't. So there will be scenarios where that's going to happen. And dealing with that, it's mainly an issue. I forgot to put my little star here as well. That is mainly an issue for sine and cosine, which are bound between, I can spell, just can't type clearly, -1 and 1. Remember, when you have just a sine of x, the biggest the answer could be is 1, the smallest it could be is -1, and the same is true of cosine. And that's because your graphs look like this, where that's a 1 and this is a -1 for sine of x, or for this, for cosine of x, where we start at 1, and go down and come back up, and then all of that value is 2 pi, that value is 2 pi. That's 1, that's a -1. That's what I mean, they're bound between. The heights are bound from 1 to -1 inclusive. I said that backwards. I should say they're bound from -1 to 1 inclusive, but it wasn't the end of the world. So we're going to see all of these little technique issues pop up, whether we're adding the 2 in pi or not doing it, whether we have to go through some of the cases or not. All of these will be seen. Your homework problems should flow similarly. Your test problems should flow similarly. So let's get to it. Remember, if you don't have the chance to write all this down, YouTube is wonderful. It's got a pause feature. So I'll kind of pull this back a little for now, but I won't be able to keep those instructions up too long. Example 1, solve. Big wordy instruction, solve. And I'm not doing A, B, C, D stuff here, so 3 sine x, excuse me, minus 2 is equal to 5 sine x minus 1. So you have seen trig equations before, but they were always very simple. It was like sine of x equals a half, or sine of x equals square root of 3 over 2, or tangent of x equals 1. This, you got to do some rearrangement to get to that point. But once we get to that point, we have gone through things like this back in that chapter 5 test. It's just a matter of putting everything in one big mixing bowl and stirring it up. So I only see one type of trig term. If there's only one trig term, just isolate it. So pretend like it's just a big, giant, fat X. Move all of them to one side, move everything else that doesn't have it to the other side. Does it matter which side the signs go to? No. Me personally, I try and keep them positive, but it's arbitrary. So I'm going to subtract 3 sine x on both sides. And with those going to the right, that means that the constants need to go left. So I'll add 1 to both sides. If you need to do that in 2 steps, be my guest. That's up to you. So those cancel and these cancel. I don't like keeping that cross out there, so just follow along. And the left side is now -2 plus 1 is going to be -1 equals 5 minus 3 is 2, so that's 2 sine x's. And the sine x is almost isolated, but we need to get rid of that 2. We do so by dividing, because what we're looking at currently is a times. And that's going to give us -1/2 is equal to sine of x. And I'm not done. I'm not saying this is the answer. I'm just pointing out this is what I mean. You have seen a problem like this previously back in chapter 5. You saw problems like this in class, homework, and on the test, where you're trying to find out what angles make this statement true. And remember, quite often, there are more than one answer to this, because sine, you can have for any angle, in quadrant 2, 3, or 4, you can take a reference angle and recreate it, and then it's just the same answer. So let's say if you ignore the plus or minus of this, if this was true for 30 degrees or 60 degrees, and spoilers, it's one of them, but I'm not saying yet, then that means you could take that 30 or 60 degrees and potentially put it in all 4 quadrants as a reference angle and potentially have 4 answers. But because of this plus or minus, sine is only negative in 2 of the quadrants, which means you'd have 2 answers, not 4, not 1, 2. All right, so sine of x equals -1/2. I'm actually going to draw up the little triangle. I know I don't do that too often. I usually pull up the other document, but let's draw it up this time. So here's your reference triangle. This will be x prime, because if that's negative, this needs to be a reference triangle. And then its opposite would be the 1, and the hypotenuse would be 2. Well, that makes this the 1, 2 square root of 3 triangle. And based on memorization of that triangle, your angle being opposite of 1 means that angle is 30 degrees, but we prefer our answers with this stuff in radians. 30 degrees is pi over 6. So that says x prime is pi over 6. Again, yes, it is 30 degrees, but we're going to stick to radians for this stuff. So that's the reference angle, but clearly the reference angle won't work because all things are positive in quadrant 1, so we need to find out where is sine negative. So we say, but sine of x is negative in quadrants, let's see, a smart trig class. Sine is the y value. When you go down, y is negative. Down is quadrants 3 and 4. So our reference angle of pi over 6, we need to put in quadrants 3 and 4. So that's going to be two solutions. Let's find the first one in quadrant 3. So let's put our pi over 6 here. So there's pi over 6. There's our reference angle in quadrant 3. Again, that angle is just there. But we need to find the actual angle, which would be starting from the positive x-axis. Now, if you're thinking in degrees, this is 30 degrees, it would be 180 plus 30 degrees, but it's in radians. 180 is pi, so that says our first solution, which I'll call x1, x sub 1, would be pi plus pi over 6, which is 6 pi over 6 plus pi over 6, just getting an LCD, which is 7 pi over 6. So that is our first solution. That is the first solution. Now let's hold on to that. What's the second solution? The second solution, we need to put that reference angle in quadrant 4 instead. So now, this is our reference angle right here of pi over 6, but we need to find the actual angle here, starting from the positive x-axis and going counterclockwise until we hit that. Now, let's think of this in radians, 30 degrees. You'd need to do 360 minus 30 to get an angle that's in quadrant 4. So we're not doing degrees there, we're doing radians. 360 is 2 pi. So that says x2 is 2 pi minus pi over 6. Again, you might need to think about this in degrees and then do your work in radians. You could also do the actual math in degrees and then convert to radians. I don't care how you get the job done. And then 2 pi, when you get an LCD of 6, will become 12 pi over 6 minus 1 pi over 6, but we don't write the 1. 12 minus 1 is 11. So that's 11 pi over 6. That's our second solution. So with those things combined, I'm just going to say x is equal to, and I'm going to do this wrong for a second. 7 pi over 6, I'm going to leave some space, comma, and then 11 pi over 6, and I'm going to leave some space. Let me write that a little smaller. Leaving some space for a reason, but if I just do this, guess what? It's wrong. Let me put the whole problem up here. I said solve. I did not give any restrictions. Sorry, my nose is stuffed up. With no restrictions, you've only given me 2 answers. And this is, what is that? 210 degrees and 330 degrees. But there's no restrictions. X can be any value. So if I add another 360 degrees, there's another answer. If I add another 360 degrees, there's another answer. If I add another 360 degrees, there's another answer. I could subtract them a million times, and there's another answer. And then I can do the same thing to the 11 pi over 6. So with this problem, because this had no restrictions, because I didn't say it was from 0 to 2 pi, something like that. That's what a restriction looks like. I did not do that, which means we have to do that thing I said earlier. The domain is not restricted, and since we were dealing with a sine, we add 2n pi to the solution. That is us just adding 360 degrees over and over and over and over and over, or subtracting 360 degrees over and over and over. So we got to go plus 2n pi to both of these. That is every single solution, infinitely many solutions in fact, two core solutions of, again, in degrees, 210 and 330. But then you can just add or subtract as many multiples of 360 degrees as you like, and then that is still true because of coterminal angles. And it's very frustrating when you're doing this as homework, and even more on a test probably, when you get this aspect and this aspect right, but then you forget to consider the domain and the whole thing's wrong. Now, again, this is another case of if you submitted your work and you emailed me and said, Mr. Beckner, I got this one wrong. Can you take a look at it? I think I had a lot of details right. I think I just forgot the 2 in pi. I can go, oh yeah, I looked at your work and you're right. Here's 4 out of 5 points, something like that maybe. Or 3 out of 5 if you made another mistake somewhere. You get the idea. But I can help you out if you show your work and point it out to me. All right. So that was example 1. No restrictions, because I did not write somewhere I would have said on something like 0 to 2 pi. That is a restriction. We will see that, but not quite yet. Example 2. Let's do tangent of x minus square root of 3 equals 0. I stopped writing. I did not write on 0 to pi or 0 to 2 pi or anything like that, so there are no restrictions, which means there should be infinitely many answers. So we're going to have to add one of those things to our cores. All right, well, I only see one single type of trig term, so it's probably in our best interest to isolate it. That's what those instructions previously said. I'll scroll back up. If there's only one trig term, isolate it. This will be a lot easier to do. You're just going to add square root of 3 to both sides. Not even going to show that work. If you add square root of 3 to both sides, I lied, I will. Since it's a radical, I'll show the work. That gives us tan x equals square root of 3. Give me a second. Okay. So again, what you can do is think about your reference triangles. Oh, square root of 3, if it's not a 0 or a 1, it's probably one of the triangles. If it's a 0 or a 1, it's probably usually a quadrantal. Tangent's the exception because when tangent's 1, that's 1 over 1, which is 45 degrees. Okay, so tangent's opposite over adjacent, but I don't see the adjacent. So remember that anytime you have just a top number, you can always write it over 1. So just note that this is the same thing as saying tan x is square root of 3 over 1. So you can see your opposite and adjacent. You can draw your reference triangle. Now I can say x or I can say x prime. Since it's positive, you might say it's just x. And you might be right for this since it's tangent, but if it was sine or cosine, it wouldn't technically be right. It would just be one of them. So let me just call it the reference angle. Opposite of square root of 3, adjacent of 1, well, that's the 1, 2 square root of 3 triangle. So that says that your reference angle is 60 degrees, also known as pi over 3. Again, you have got to be able to go between radians and degrees like that for things like 30, 45, and 60, and 90, and 180, and 360. Now the question is the reference angle one of the solutions? Well, since this is positive, tangent is positive in quadrants 1 and 4. I said that wrong. Tangent is positive in quadrants 1 and 3. I was thinking of cosine for some reason. I don't know why I had cosine in my head, but tangent is positive in quadrants 1 and 3, based on a smart trig class. A, all, quadrant 1, all, so tangent. Smart trig, T, tan, quadrant 3, positive. So here's where things get interesting. tangent's positive in quadrant 1 and 3, so normally we'd have to take this angle, put it in quadrant 3, and then go from there. Take the reference angle, put it in quadrant 3, and then you'd get, what, 4 pi over 3. But here's the thing. We're only going to consider quadrants 1 and 2 for tangent, since its period is 0 to 2 pi. 0 to pi. Why do I keep putting cosine in my head for some reason? It's awful of me. It has a period of pi. So you get to pi by quadrant 2. That's weird. So that's just quadrant 1 and 2. So we're not actually going to worry about putting our reference angle in quadrant 3 because, let's scroll back up a little. We said for tangent and cotangent, you don't add 2 n pi, which was 360, you add n pi, which is 180, so just multiples of 180. So any answer that's in quadrant 1, when you add 180 degrees, you're going to put it in quadrant 3. And then from quadrant 3, when you add 180 degrees, you'll go back to quadrant 1. So you'll keep bouncing back and forth between quadrant 1 and 3. So you would actually be not wrong, but redundant if you put your reference angle in quadrant 3 and said that was the second core solution. I'm making quotes with my fingers there that you can't see. And you would actually label 2 different sets of solutions, and my math lab would mark it wrong. I could go back and say, well, here's 4 out of 5 points because that's technically correct. It's just written in a goofy way. So that's why you need to understand with tangent, you only worry about quadrant 1 and 2. All right, so that says x prime. Oops, back to black. So the first solution is x prime, which is pi over 3. There's no need to put that in quadrant 3, as we've already talked about. When we add the n pi, it'll pick it up. With no restrictions, so the actual solution is pi over 3 plus n pi. Again, that is we're taking 60 degrees and then adding 180 to find the next. 60 plus 180 is 240, and that's exactly what you would get if you put your reference angle of 60 in quadrant 3, because 180 plus 60 is 240. So that 240 is picked up right here when n is 1. When n is 2, you'll end up getting 420. When n is 3, you'll end up getting 600. And then 780, et cetera, et cetera, et cetera. And you can go into the negative angles as well. You can subtract 180, 360, 540, 720. All right. So that was example 2. I'm going to highlight this memo for a second because it's about to be relative. I'm going to write something else regarding that. If the inside of the function is not just an x, you're going to need to go through some cases of your n. And what you might even want to do is a substitution. A lot of people struggle with this if they don't do this substitution technique I'm about to show you, because, well, let's just find out. So when inside is 2x or 3x, etc., a substitution is a great idea. In other words, you're going to say, let theta equal to, and then whatever the inside was. If it was 2x, let theta be 2x. If it was 3x, let theta be 3x. There we go. Then, Find all theta values that work, then convert back to x, and only then do the n equals 0, 1, 2, 3 until you're outside 360 degrees. Or the other restrictions. Final memo for this. Make sure, and in all caps, because the order you do this matters, you add the n pi or 2n pi. I'm not saying divide, I'm saying whichever it is, in the theta solution. 5 exclamation marks. This is the thing that people get wrong. By this I mean when you add the 2n pi or the n pi part. A lot of people will just do it at the very end once they have the x equals, and that's where they want to add it. But that's not true. You have to put it where you have theta equals, because the solutions that you find will be based on your substitution, and the substitution solutions will be every 360 degrees or every 180 degrees, whatever. When you go back to your x, that multiplier actually has an effect. Remember when we were graphing sine of x versus sine of 2x versus sine of 4x, the number in front of x made one waveform happen quicker. So if one wave happens in 360 degrees for sine of 2x, that wave happened in 180 degrees. Sine of 4x would happen in 90 degrees. Sine of 8x would happen, you get a full period every 45 degrees. So that multiplier inside of a trig function changes things. But when you're in the substitution, when you're in theta, you're thinking about everything happening in 360 degrees, but when you go back to x, things could happen in less than 360 degrees. And that's why you have to do that addition before the final part. So what I'm going to do is I'm going to do an example 3 with an a and a b. It's going to be literally the same equation. One of them I won't give a restriction, then the next one I will, and we'll compare and contrast. All right, so example 3. This is where it starts getting a little weirder. For a, and all the instructions are solve. Sine of 2x is equal to negative square root of 3 over 2. That's the whole problem. There's no restrictions. The inside is not just an x or a y or a theta or whatever. It's a 2 something, 3 something, 4 something. That is what we were just discussing. So what you need to do is you need to say, to make this easy on yourself, let theta or whatever letter you like equal the inside. This should not be the first time you've ever done a substitution technique. We do that in 2 different types of problems in pre-calc 1. So now what this problem is going to become is, and I'll keep it in blue since I'm doing a change of variables, it's now just the sine of theta is equal to negative square root of 3 over 2. Well, we can draw up our little reference triangle, or if we already drew it somewhere else, we could just pull from there. That's a negative, so this is definitely a reference theta. And its opposite would be the square root of 3. The hypotenuse would be the 2. This is the 1, 2 square root of 3 triangle that you should have memorized. Since it's opposite the square root of 3, that makes this the 60-degree angle, which is pi over 3. So the reference angle, which could be a solution, maybe it is, maybe it isn't, is pi over 3. That is not a solution to the original equation. That's a solution in this new variable. We went from dollars to yen. So the answer in yen might be 500, but that's not the answer in dollars. You'd have to convert it. And a yen is about a penny roughly, so it'd be about $5. And again, that's roughly. It's not quite 1 to 100 anymore, but not the point of the problem. So that's our reference angle, but sine is negative here. So sine is negative. Let's see, us smart trig class. So it's positive in quadrant 1 and positive in quadrant 2, which means it's negative in quadrants 3 and 4. So we need to put our reference angles in quadrant 3 and 4. So if we draw up a reference angle in quadrant 3, it would look something like that. Here is our pi over 3, and then our actual angle would be going from 0 to there, which would be pi plus pi over 3. So the first solution would be the pi over 3 plus pi. The order you write them doesn't matter. I usually write the pi first. Got to get an LCD. Told you it's never going away. That's 3 pi over 3 plus pi over 3, which is 4 pi over 3. Then let's put a reference angle in quadrant 4. So here's our pi over 3, meaning the actual angle swings till here, which is that 360 minus the angle case. 360 is 2 pi. So our second solution would be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, which is 5 pi over 3. Now, some people will stop here. They say, oh, 4 pi over 3 and 5 pi over 3, and that's wrong. First of all, there are no restrictions, so you're forgetting to add the 2 in pi. All right, so the next student, the student remembers, oh, okay, I got to remember to add the in pi. Remember, I even had this all capitalized. Make sure you add the in pi or 2 in pi in the theta solution. So that's where these need to go. So now what we can say is, putting all of that together, so our theta solutions are 4 pi over 3 plus sine has a period of 2 pi, so adding 2 in pi, or it can be the 5 pi over 3 plus the 2 in pi. And then somebody boxes this up and ships it out, and they get it wrong because you're still in yen, and I asked you a question in dollars. Oops, drop something. So we're not done yet. Let's go back to our little instructions. So you find all the theta that work. We've done that. We found all infinitely many angles that would solve this thing in terms of yen, but we want it in terms of dollars. So now we have to convert back to X. And then this only blah, blah, blah part, this may not even be an issue. Like I said, it's based on restrictions, and we didn't have restrictions, so maybe it's a non-issue. So let's convert back to X. We said that theta was 2x. So now instead of writing thetas, let's write 2x instead. So now we go back to X. So I'll use a different color. So instead of writing theta equals blah, 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 we write 2x equals blah, blah, blah. 4 pi over 3 plus 2 in pi. And then the other one would be 5 pi, oops, blah, 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 blah. I forgot the theta equals. So 4. And the theta part would be 2x equals 5 pi over 3 plus 2 in pi. Here's the first one, theta equals this part. That was this, not just the 2 in pi. And then this one is this equation. These used to say theta equals, now they say 2x equals because theta is literally 2x. We made that decision. Now all we do is solve for x, which is literally nothing to do. You just divide each thing by 2. Divide each thing by 2. But notice something. If you didn't put this plus 2 in pi originally, if you waited to the last second, you would just write a plus 2 in pi once you have your x equals. That is not what you're going to see for the actual answer, though. So when you do these divisions, you get x for the first one. 4 pi divided by 3 divided by 2 ends up being 4 pi over 6, which reduces to 2 pi over 3. I'm going to show that arithmetic in a minute. So 2 pi over 3. Again, that's what this becomes. I'll show the arithmetic in a hot second. But these 2's will just directly cancel to get you a plus in pi. And then, or it would be x equals, those 2's canceled. This 5 pi over 3 divided by 2, this turns out it's 5 pi over 6. And then these 2's will cancel with the in pi. These are our solutions. So infinitely many solutions, but it doesn't have a period of 2 pi. This says that it has a period of pi. So these solutions are occurring every 180 degrees, every multiple of 180 degrees. So these are periodic in pi, not 2 pi. And the reason for that is because this 2 here makes the period happen quicker. It happens twice as fast. If that had been 3, it would have happened 3 times as fast. So then your period would end up being 2 pi over 3. All right, so where did this math come from? All right, the 4 pi, let's just squeeze it over here. 4 pi over 3 divided by, that's divided by 2 over 1, 2 over 1. So that's 4 pi over 3 times 1 over 2, and then the 4 reduces to a 1, and the 2 reduces to a 1, giving you, the 4 reduces to a 2, excuse me, your 2 pi over 3. For the 5 pi over 3 divided by the 2, that's divided by 2 over 1, so that's 5 pi over 3 times a half, which clearly gives you your 5 pi over 6. Now, I did not go through n equals 0, n equals 1 equals 2, any of that stuff, because this problem did not have any restrictions. So again, this whole little, let the n equals 0, 1, 2, 3 is only if you have restrictions. Notice I said, or other restrictions. So that's why I did not do anything having to do with n equals 0, 1, 2, or 3 here, because this problem had no restrictions. Now what I said is I'm going to take this exact same problem and I'm going to give it a restriction, the same restriction we've already seen at least once. I'm going to say it's bounded from 0 to 2 pi. All right, so for B, we're going to solve sine of 2x. Equals, what was it, negative? I think so, yeah, negative square root of 3 over 2. But now it's going to be on 0 to 2 pi. There are several different ways that we can label the restrictions. This is using interval notation, which is my favorite way, but they could just say under 1 full revolution, which would imply the exact same thing. Now, you might say, oh, okay, well, do I need to do the whole let theta equal this, reference triangle, get the pi over 3, but that's a reference angle, put in quadrant 3 and 4. No, this is literally the same problem as A. It's just this is the only thing that's changed. So if I were to do this on a test, what you could do is you can just say, by example 1A, or by problem 14 on the test, we know the solutions in general are x equals 2 pi over 3 plus n pi, not 2n pi. Again, if you had put the 2n pi in there for the x part and not the theta part, that would have been your mistake. You would still have this part and this part right, but you wouldn't have divided the 2 out, so you would have missed it over here and here. And that is a massive mistake because you'd only have half of the solutions. So we know in general x equals 2 pi over 3 plus n pi and 5 pi over 6 plus n pi. So we're just going to take that, but with the restrictions. So 2 pi over 3 is an answer, then 5 pi over 6 is an answer. And then there'll be another answer if we add 180 degrees, and there'll be another answer if we add 180 degrees to this one. And then maybe there's another one if we add another 180, and another one we add another 180. So we just need to actually go through n equals 0, 1, and 2 until we get answers that are bigger than 2 pi. So with the restrictions, we just let n equals 0, 1, 2, 3, da 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 da, until we're past 2 pi. So if we let n equals 0, the first case is letting n be 0. So we're just going to both of these things. We're just making this n a 0 and this n a 0. Well, adding 0 does nothing, so you just get 2 pi over 3 and 5 pi over 6. There's two solutions. Now let's try plugging in n equals 1. N. Plug in to n 1. So now those n's over here are just becoming 1s. We're just running through all possible cases. That's all we're doing. So x equals 2 pi over 3 plus 1 pi and 5 pi over 6 plus 1 pi. Let's get LCDs. So that's 2 pi over 3 plus 3 pi over 3, then comma, 5 pi over 6 plus 6 pi over 6. 2 plus 3 is 5, so that's 5 pi over 3 for the one in front of the comma. 5 plus 6 is 11, so that's 11 pi over 6 for the one after the comma. So that's 2 more solutions for a total of 4 thus far. Now, you've got to start asking yourself, are these too big? Are either of these solutions bigger than 2 pi? Or even if they are 2 pi, that's too big because that's an open-ended restriction. So 2 pi is not included. But 5 pi over 3, 5 divided by 3 is 1 2/3, so that's fine. 11 divided by 6 is 1 5/6, so that's fine. It's just if you divided those and you got a number bigger than 2, or if you even got 2 exactly, it's too big. So let's try n equals 2. Now I can actually tell we're going to get past solutions that work, because if I add another 180 degrees, because every time we add another pi, we're adding another 180 degrees. So adding pi for n equals 1 made us 180 degrees past it. So if we started at, say, 2 pi over 3 is what, 120, adding 180 to that is 300. If you add another 180 to 300, that's too big. It might not be so clear in radians, so someone may do this legwork. Same thing for this. If you add another 180 degrees to this, you're definitely past 360. So 2 pi over 3 plus 2 pi now, again, that 1 for the n is now a 2, or it could be 5 pi over 6 plus 2 pi. I'm going to skip showing the LCD work. You're just going to end up getting, what's that, 6, so that's 8 pi over 3, That's 12 and comma 17 pi over 3. 8 divided by 3 is bigger than 2. 17 divided by 6, not 3, excuse me. 17 pi over 6. These are both too big. So that means we only get 4 solutions. We get x equals 2 pi over 3, 5 pi over 6, 5 pi over 3, and 11 pi over 6. That's a long problem because in doing this problem, we didn't even do half of the work because I borrowed it from a previous example. Imagine if I hadn't done it that way, we'd still be working on the problem. So when the inside is not just an x or a theta or a y or just a single letter, if there's a multiplier there, it complicates things more than anything else in this entire section, in my opinion. Because you have this substitution to run through, you have to make sure that you add your periodic nature at the appropriate point. So in the substitution part, not the final part, because the final part has to take that 2 into account, and it causes it, again, to speed up. Things happen twice as fast or 3 times as fast. So this additive periodic nature value changes. It gets smaller. Sure I didn't, we're good, okay. So that's the first major complication. The second major complication is if I give you one where you have the number inside and I give you restrictions, holy cow, that's a pain in the butt. That's a long problem, but it's a perfectly valid problem, and it's something that you have to understand to be able to reason through. So you've got to do your if this was a completely new problem, I'd do my substitution. I'd find my solutions in theta. Then I would add the 2 in pi because it's sine. Then I'd go back to x. Then, because of the restrictions, I have to go through n equals 0, 1, 2, 3, et cetera, et cetera, et cetera. There's a lot of details here to keep up with. Now, am I going to throw 5 of those on a test? Absolutely not. It would be 1 of them at most, and that is definitely a 1 at most. So let's do something different. For example 4. Let's take something that looks like this. 2 sine of x plus 1 times 2 cosine of x minus the square root of 3. Then equals 0. And we're going to solve this on 0 to 2 pi. So I am giving you restrictions. I'm telling you the #1 mistake students make is they don't pay attention to restrictions. I'll give them restrictions and then they'll add the 2 in pi at the end, or I won't give them restrictions and they forget to add the 2 in pi at the end. But that one little detail will make it go from right to wrong in the snap of a finger. And again, on a test, you show your work, you point it out, you could get partial credit, but homework, it just means you're going to have to do it again, and that's a headache. Especially if you miss it 3 times in a row, and then you got to start over. So one of the instructions, let's go back to the instructions for just a minute, said to factor if possible. We have gone through the, if there's only one trig term isolated, we've gone through the, we might have to do a substitution and a n equals 0, 1, 2, 3 stuff. We've done all that. The next one is factor if possible, because there might be like a sine squared somewhere, or there might be just a GCF potentially. That's what I'm starting to get into. And when you have a factored equation, you set each factor equal to 0. Well, I gave this to you pre-factored, so that's nice. But because it's factored, we follow that 0 product rule. Which says we can just set each factor equal to 0 on its own. So we can set the 2 sine of x plus 1 equal to 0. That'll be its own thing. And then let me give myself just enough space. And then we set the other thing, which is 2 cosine of x minus the square root of 3 equal to 0. That's old algebra. So this is two equations that we have to solve. Pay attention to reference angles, a smart trig class, remembering restrictions, so we're not going to be adding a 2n pi here. Now, even if there are no restrictions with those substitutions, we still had to do it. I mean, even if there are restrictions, we still had to do it. Let me point that out. So back on this example, there are restrictions here, so you might think, oh, I don't have to add that 2n pi bit, but yes, you do. Whenever you have a multiplier inside, even if it's restricted, you have to add the 2n pi or n pi, whichever is relative. And you have to remember to add it for the theta section, not the final x section. It's a lot to keep intact in an order. All right, so let's just subtract 1 on both sides. You'll get 2 sine of x equals -1. Divide both sides by 2. You get sine of x equals -1/2. Let's go ahead and clean up this other one. Add square root of 3 to both sides. You get 2 cosine of x equals square root of 3. Divide both sides by 2, and you get that the cosine of x has to be square root of 3 over 2. See, these don't end up being just random numbers. We end up seeing a lot of these same familiar numbers. Square root of 3 over 2, 1/2. Square root of 2 over 2, or 1 over square root of 2 maybe that you could clean up. 1, 0, -1. Those are the types of numbers we should anticipate to see, because I'm not going to give you something that you need a calculator for and to get a decimal approximation to. I'm giving you something that you can use your quadrantals, your 30, 60, 90, and your 45, 45, 90 triangles. I could be mean and make it so you need double angle formulas, half angle formulas, maybe a 15 degrees is involved. I'm not doing that. That would be torture in trig class, a regular trig class. All right, so where is sine of x equal to -1/2? Why does this seem so familiar? Why does this one right here just sound so familiar? I feel like if I scratch my brain hard enough, it sounds weird, doesn't it? But I like it. If I scratch hard enough, maybe just let me see. What do we do? Sine of no, no, no. Oh, this is why it seems familiar. Sine of x equals -1/2. We have already found the solutions to that. So this is another case of, if on a test, if I gave you one problem that was simpler and you got this, and another problem you've got more going on, and you notice something that you've already done before, don't reinvent the wheel. You can just say, by example 1, so by example 1, we know x is equal to, now those solutions were, shoot. Sorry about that. I should have put them in my brain. I scratched too hard. 7 pi over 6 and 11 pi over 6 plus their 2n pi's. Now this example was not restricted, so it had the plus 2n pi's. This one is restricted, so we don't need to add the 2n pi's. There's no extra little 2 or 3 inside, so we don't have to go through the cases. So it's just 7 pi over 6 and 11 pi over 6. Again, I do not need to add the plus 2n pi's because we are restricting this time. And there was no 2 or 3 or 4 inside with that x. Those are the things that make us need to add the plus 2n pi. Big time-saving element. Feel free to use that on a test whenever you can. So there we go. That one's done. This one, however, we have not seen. We're going to have to do the legwork. So, all right, cosine of x equals square root of 3 over 2. Let's draw our reference triangle. And again, we're considering all 4 quadrants. So even if this is a solution, I'm going to call it a reference angle for now. Adjacent should be square root of 3. The hypotenuse should be 2. That makes the opposite 1 because it's the 1, 2 square root of 3 triangle we've memorized. You can do Pythagorean to figure it out, but you should memorize that one. So that says x prime, since it's opposite the 1, that's the 30 degrees, which is pi over 6. Now cosine, this is positive, Cosine is positive in quadrants 1 and 4 based on a smart trig class. A, all for quadrant 1, C in quadrant 4 for cosine. So cosine is positive in quadrant 1 and 4. So that means our first solution over here, it's technically the third solution, but I'm just going to write a little 1 here, is pi over 6. And then the second solution we got to put in quadrant 4. So let's draw our angle in quadrant 4. So here's our pi over 6. But our actual angle will go all the way around this way, which would be 2 pi minus pi over 6. So x2, 2 pi minus pi over 6, which is 12 pi over 12 minus pi over 6, which is 11 pi over 6. So the solutions from this one are pi over 6 and 11 pi over 6. But our solutions are all of them, not just the sines problem, not just the cosines problem, it's all of these. But look really carefully. What do you notice? That's right, that you answered to yourself, I hope. 11 pi over 6, 11 pi over 6. We saw the same solution twice. Do we really need to write the same solution twice? No, we don't. So since we have an overlap, we're only going to write it once. So we just say for the solution x equals, and I'll put them as in, I'll even put them in ascending order. You don't have to, but I'm going to, is pi over 6, 7 pi over 6, and 11 pi over 6. That is the solution. There's no +2 in pi's or in pi's or any of that because there were no, because there were restrictions, and there were no 2x's or 3x's inside of the trig functions. So the 11 pi over 6 just happened twice. It was seen twice. There's no need to write it twice. All right, I think we have time for one more and we'll call it a day. But let's just re-look at this because the next problem eventually we'll get to this, what it started as, not the same thing, but just the type of parentheses, zero product rule, and you'll have two different equations to work through. Do you see why I tried to emphasize so heavily back in chapter 5 that if you don't learn chapter 5, you can't do anything in this course? Because this right here was a problem in chapter 5 that people already struggled with. And now that's not even like 1/4 of the problem itself. It's like chapter 5 is us learning how to add, subtract, multiply, and divide. And then chapter 6 and on is us trying to solve equations with that stuff and simplify fractions and decimals with that stuff. Again, I'm not saying that's the process. I'm just giving you a similar relationship. I think I can fit example 5 here. Solve 2 cosine squared x, that's a first today, plus cosine x minus 1 equals 0, and we're going to do this on 0 to 2 pi. The restrictions do not have to be 0 to 2 pi, but it is a common restriction because then we're just saying one full circle. That's the most common type of restriction. And it's the way most of us tend to think, but again, in the grand scheme of things, without the restriction, we're supposed to think of the infinitely many answers that are possible. It's kind of like saying, all right, if you have $50,000 worth of bills, how much money do you need to make? And someone says $50,000. No, that's not true. That's one answer. You could make $51,000, $59,000, $59,273.14 after Uncle Sam takes his taxes and whatever. There are infinitely many answers to that problem. You don't have to make exactly 50,000. The answer would be 50,000 or more. All right. So back to the instructions. Scrolling, we're scrolling, we're scrolling. Factor if possible. Now you might say, well, what about Pythagorean? Use Pythagorean. Would that be helpful? Question mark? Because I saw cosine squared. Maybe we want to make that 1 minus sine squared. So someone will see this cosine squared and say, should we make that 1 minus sine squared? If this was a sine, I would say, yes, do that. If this term was also a sine, I would say to do that so that then you would have everything in terms of just one trig function. However, we're already in terms of one trig function, so Pythagorean might not actually help us. Instead, what we want to do to start this is factor. So if you need to show a substitution, this is like thinking about, this is a similar problem, 2x squared plus cosine of x minus 1 equals 0. This is basically what we're factoring, it's just I'm calling this x and this x. Or you can make them y's, so they're different letters and you're doing an actual substitution, however you need to do it, but this is just ordinary factoring. You can AC method it, you can trial and error it, and I wrote cosine there, didn't I? Because I have cosine stuck in my brain. That should have been just a x. There we go, now it's right. Sorry for that. So with a 2x squared, the only possibility the first terms can be are 2x and x. With that being a 1, the only possibility is those to be 1s. Trial and error is ridiculously short here. And then in order for the outer and inner to come to a positive 1, the larger product needs to be positive, which is the outer product, which makes a 2x. So that'll be the plus. This has to be the minus. Again, factoring is on you. If you're rusty with factoring, go do 100 or 1,000 of them. So what I'm going to do is I'm going to just say, instead of writing x's, I'm writing cosines. So the factored form is 2 cosine of x minus 1 times cosine of x plus 1 equals 0. Some of you may not even do this blue stuff over here and go straight to that. That's perfectly fine. Some of you need to see this in a simpler looking form and would do the blue version. That is also fine. Do I care which way you do it? Nope. I care that you can get it done with a way that works always. All right, 0 product rule this bad boy, or bad girl, whichever. So we get 2 cosine of x minus 1 equals 0. Or we get cosine of x plus 1 equals 0. Give me 15 seconds. All right, basic algebra. Add 1 to both sides, you'll get 2 cosine of x equals 1. Divide by 2, you'll get cosine of x equals a half. Make my equals a little nicer, and my s. For the other one, you just got to subtract 1 on both sides, and you get cosine of x equals negative 1. All right, one of these equations at a time. So let's just focus on cosine of x equals a half. Well, let's draw up a reference triangle, or use whatever one you've already drawn, the two that you've already got drawn, however you're doing this. Here's our reference angle. Adjacent is 1, hypotenuse is 2. Well, that's the 1, 2, square root of 3 triangle once again. I love that triangle. I love it more than the 45, 45, 90, because at least the cosine and sine are different. For 45, sine and cosine are the same, so you can kind of cheat the system, maybe. So that says x prime has to be, since it's opposite the square root of 3, that's 60 degrees, also known as pi over 3. Now cosine, this is a positive half. Cosine's positive in quadrant 1 and 4 based on a smart trig class. So that says the prime angle, the reference angle, is the first one. But the second one we'll have to put in quadrant 4. So we put our reference angle in quadrant 4. Here's our pi over 3, but our actual angle would swing all the way around, which ends up being 2 pi minus pi over 3. So x2 equals 2 pi minus pi over 3, which is LCD of 3, so that's 6 pi over 3 minus pi over 3, which is 5 pi over 3. Now there were restrictions on this. We were from 0 to 2 pi, so I don't have to add the 2 n pi to these solutions. We got pi over 3, and we got 5 pi over 3. So far, we have pi over 3 and 5 pi over 3 as our answers. Those are the only two solutions to the cosine x equals a half from 0 to 360. But we're not done. We have the second equation, cosine of x equals negative 1. And you might say, we'll make that a 1 over 1, and then you try to draw a triangle where the adjacent's 1 and the hypotenuse is 1, and that triangle literally doesn't exist. So you have to remember, wait a minute. When you have a sine or cosine equal to 0, 1, or -1, that's a quadrantal. So you go back to, all right, well, where is cosine negative? Well, cosine goes like x, the x coordinate on the unit circle, and -1 is right here. That's our -1 comma 0. The x coordinate's -1. In terms of an angle, that's 180 degrees. So x has to be equal to pi, 180 degrees. There is not a second solution to that. And that's pretty common for the quadrantals unless it's a 0. If this was cosine x equals 0, then we would have answers of pi over 2 and 3 pi over 2, since this is 0 comma 1, positive 1 there, and then this point is 0 comma -1. So if this was cosine x equals 0, you would get 2 solutions of pi over 2 and 3 pi over 2. But the 1 or -1, those only happen once for the quadrantals. So here is our third solution. So we got x equals, for all of them together, pi over 3, that was our first one. I'm going to put these in order. Pi occurs next. They don't have to be in order unless it says, and I don't think it tells you to do it that way. And then 5 pi over 3. Again, if there were no restrictions, I would be adding 2n pi to each of these. There were no restrictions, so we're done. So that is all the time we have today. We have a few minutes left, but like I said, there's no way we can finish example 6 with only 5 minutes remaining. So when we come back next time, we'll have examples 6, 7, 8, and 9. So we got 4 left. One of them's a little weird, admittedly, but we'll figure out why it's weird. Another one is weird in the thing I said not to do to this problem. We said, oh, I saw a cosine squared, so maybe I want to write that as 1 minus sine squared. But I said, don't do that because these are already the same trig term. If they're different terms, then you would want to do that. Spoilers for example 8. All right. So on that note, if you have any questions, please email me. We are on perfect pace right now to get the test done on the dates I prescribed, that Monday and Tuesday, which were, what, the 9th and 10th? Yes. So I do anticipate that our test 2 on chapter 6, excluding 6.4, will be on Monday the 9th and Tuesday the 10th of November. You'll get a review for it. You'll have a decent amount of time with the review posted for you to work on that. The review will be similar to the test. The test will be 90 minutes. No more than 20 questions, but probably in the ballpark of 15 since there are some long problems with this material. But we'll get more details later. Besides that, have a good one. Have a good weekend. Work hard. Put in the time. Put in the effort. Stay motivated. Have a good day.